Okay, Kepler's a guy that lived a long time ago. He's an old dead guy. And he was studying the motion of planets and such like that. And he came up with a few laws of motion, a few of which we want to use. And one of Kepler's laws is that the planets and anything that's orbiting a body has an elliptical orbit. Well, it turns out that the Earth is a special body. So the Earth around the sun, the Earth actually has an almost perfectly circular orbit. Okay, now a circle is just a special case of an ellipse. So that's why it works for the Earth. It's still an ellipse, it's just a special case. And it's a good thing for us that the Earth does have a almost circular orbit, because that means that no matter where we are around the Earth or around the sun, we're about the same distance no matter where we are. And that means we're getting the same amount of the sun's heat, the heat and the energy from the sun. If we were this poor planet over here, then when we were in this spot, we'd be way far away from the sun's heat and it would all disappear. But if we were in this spot right here, we'd be really close and we'd be zapped. So this would be really hot and this would be really cold. And this is a lot different than summer, winter, because you would have hot twice a year and you would have super cold twice a year. Okay? When you were on the far elliptical parts of your motion, you'd have your cold a few times a year. And actually, one of the mass bodies, you know, an ellipse has two foci. Those are those fancy math words. It has two foci. The sun here would actually be in one of those foci. So you could be super close to the sun over here. You'd be super close to the sun because the sun would be like here. And then you'd be super far away from the sun. So super close, super far away. Because the sun, the object that everybody's orbiting is at one of the foci of our ellipse. Okay, another law of Kepler's is that when the planet is in an elliptical orbit, and here's our sun here at one of the foci, it sweeps out equal areas. So this area here and this area here are the same if these times are the same. So it sweeps out equal areas in the same amount of time. Now, the consequence of this is that as the planet is really close to our Earth, or our orbiting our center object, so when I'm really close, I've got to sweep out this whole distance because I got to cover all that area. So I'm going to be going faster here than I'm going right here because I'm going to cover only that distance in that time, but I'm going to cover this whole distance here in the same amount of time. So the consequence is that the planetary object moves faster as it gets closer to the sun. And then the last one, that's the one that's going to be important to us, has to do with how long it takes the planet to go around the sun. So if here's our sun, and here's our planet, and then we have another planet that's way out here. The time it takes for one planet to go around. So the time it takes for this green planet to go around, also known as its period, is related to its radius. So this is its radius. And it is sort of proportional to this guy's period here. But what we know is that the period, this is a really weird relationship. This is a period squared is proportional to, that's what the little alpha thing means, the radius cubed. So it's not like a one-to-one thing, and it's more weird like this. But this is the bottom line, and we can actually figure that relationship out in an equation which both classes are going to have to use. Okay, so remember that our velocity is 2 pi times the radius divided by the time. Okay, that time is the period. So it's the time for one distance, the distance for one cycle, and the time for one cycle. So that would be our velocity. But we also derived the equation that the velocity was equal to the square root of big G times m, the mass of the middle object, over r. So these guys are equal to each other. Okay, so it comes from this equivalence here. And so if we solve it, you can see the r squares and the r cubes as we go along. So let's get rid of this square root. We don't like square roots in equations, so let's get rid of that square root. We're going to square this side. And when we square this side, we get 4 pi squared r squared over t squared is equal to gm over r. And then if we get all the numbers on one side, so let's get G and M and 4 and pi all on one side, and then we have T and R on the other side. So we'll put R over on the left side, and we'll have 4. That was ugly. Sorry about that, guys. We will have 4 pi squared r cubed. Oops, I made a mistake here. This is supposed to be t squared. You didn't catch that? Over, this is cubed. Boy, I'm making all kinds of problems, aren't I? This is cubed because we took the r and brought it up there. So let's write it pretty. Come on. R cubed over t squared is equal to gm. And then put the 4, move that over to the other side. So we have r cubed over t squared equals gm over 4 pi squared. And what that does is it shows us that the period squared, just like we said before, the period squared is proportional to the radius cubed. And that's where that idea comes from. The period squared is proportional to the radius cubed. And this, oops, is it in equation form. Good? All right, so now we're going to go apply that, and I'll give you lots of help. Don't worry about it. See you later. Bye-bye.